Ladies and gentlemen, thank you being here attending my presentation in this afternoon. I am Xiangnan and come from Institute of Mechanical Chinese Academy of Science. Today I will share our recent research viewpoint and ongoing work about how to assessing high cycle and very high cycle fatigue of titanium alloy with additive and conventional manufacture just with a microstructure based tensile indicator. This is the outline and introduction, how to use a few easy obtained quantity to assessing the fatigue performance. The second part about the basic information about titanium alloy, and the third is the result of high cycle and very high cycle fatigue, and the last is the viewpoint. It is well known that the assess the fatigue performance for a material is very hard thing because you hope to obtain the whole SN data, and only the SN data is very time consuming and money consuming. Even for one stress ratio, you need at least 10 or 15 specimen. And a specimen only account 1 point. So it's very difficult to obtain. But the tensile curve is very easy to obtain. One specimen you can just conduct a tensile curve, and the tensile curve usually didn't depend on the specimen size, and with small scatterness. So in traditionally people just use the UTS to assess the fatigue limit, the traditional fatigue limit, and the fatigue limit always show a linear relationship just versus the UTS. So the ratio, the just fatigue limit, traditional fatigue limit to the UTS called fatigue ratio. It's well known in engineering and scientists, but as mentioned yesterday, Professor Poliloka, very high cycle fatigue occurred when the material during 10 million cycles. We can see this surface just show the linear relation, but just for surface type fracture, but for the interior fracture, just with fish eye, and no depend on the tensile strength. So the question is how to easily and quickly assess the very high cycle fatigue performance. This is the Professor Sakai's result. Can easy find the duplex SN curve, and for the high cycle regime, the fatigue surface just from specimen surface, and for the with the filler cycle increase, then the crack just shift to specimen interior, and with a fish eye morphology. So I can ask a question for these three state material. See also titanium alloy, but different microstructure. Who is the best one for very high cycle fatigue? This just show the this tensile strength, this like this different UTS and different elongation. Now I show the basic information about titanium alloy. Titanium alloy have two basic solid state phase. One is alpha in room temperature, and the other is beta in high temperature. Just show this is a simplified phase diagram. You can, based on the beta content, they call near alpha plus beta, metasphere beta and the beta. In this work, we only focus on near alpha and alpha plus beta type. For near alpha and alpha plus beta, only 4 basic microstructure called equiaxial microstructure, bimodal microstructure, and the laminar microstructure, and the basket weave microstructure. And the basket weave also from the forged state, and the laminar is the laminar and the equiaxial is based. The key is in the alpha phase. The alpha phase is shape. For equiaxial and bimodal microstructure in the alpha phase, that is existed in the equiaxial alpha grid. But for laminar microstructure, only laminar shape. Even for additively manufacturing, the laser spatter just in interaction with powder and powder particle, and then the melt pool behavior just introduce so many AM defectors, just like depth of fusion and porosity and keyhole and another thing. And then the cooling speed is very quickly. So the just show the phase transformation from liquid to beta phase to alpha phase, just to show the laminar microstructure. And equiaxial alpha grid only from recrystallization we can obtain. This is our high cycle and very high cycle fatigue lab. This show we use an ultrasonic device. Just this figure just for the -1 means symmetric push pull, and we use the gas, the cool gas to cooling the specimen during the loading. This show the specimen size. And this when we need a tensile strength, we just connect the specimen, and then the tensile machine can perform the uniform tension force. Now we talk about the tensile plasticity on equiaxial microstructure. We developed a method based on pre-torsion, just like this. This is the specimen. We fix the end and the torsion at the other end. We can find this figure showing the surface microstructure and the alpha green distribution, and in the interior we can see the almost flat greatly, and we can find this method can modulate the tensile behavior. We can see just like this. The fracture always from surface grade, and just shift to the specimen interior. And we also talk the specimen surface roughness on the equiaxial microstructure. We can see the different roughness effector, but and then the specimen always from specimen surface, and the upper border called the intrinsic one, and the additively manufactured the result just like this. Also show the column beta green and RM column, and we after HIP treat the void just disappeared and shape several inclusions, and the microstructure also the RM only secret. We also talk the result, the result about very high cycle in the just like this, and compared to the forged state, and laminar result from just from our research. So I can answer the question just like this. Exactly in the very high cycle stage in the EM is the best. The ES and since the HIP and the failed by the inter-track initiation just like this. So my result, the plasticity is important, and the plasticity is a key role. And make advertise. Now I am Dr. Abilisio just for a special issue for fatigue and fracture topic. We can welcome to submit it, and thank you.